Welcome to Oxprune, the technology magazine. Hello, and welcome. I want to talk about belt drives today. We encounter belt drives practically everywhere we look. They are present in conveyor belt systems and form part of elevator installations. Furthermore, we find them within the automotive industry, or even in agricultural machinery, and also in the field of three-dimensional printing. So really, in a whole range of industries, that is where we come across belt drives. This is for a very good reason, as they are highly efficient, operate quietly, and when properly implemented, they also offer longevity. What is a belt drive, and how do we picture it? I have brought a model with me that is sitting here on my table. This is, of course, a very small model. It is a demonstration model, nothing that you would find in this size in practice. But to understand it, it is perfectly sufficient. What do we have? We have a control unit. We have an electric motor here, a small electric motor, which drives a toothed belt via a belt pulley. And situated on a shaft here, we have a second belt pulley, which in turn is connected via the shaft to a secondary system, a second belt system right here. Let us examine these belt pulleys now. And if we look at them from the side, then we see the teeth at the front here, this structure, where the friction essentially takes place, where power is transmitted. So much for the theory. Now let us get the system running. I am now gradually increasing the speed here. And we can see that it is starting up. And indeed, we observe that the motor drives this belt pulley and via the shaft. The power transfer reaches this second shaft. Therefore, we have a transmission here. And because it is a bit loud, I will reduce the speed a little bit again. To better understand the principle, we need two more technical terms. When we look at the system once more, we see that the motor is pulling the belt towards itself down here. Therefore, this side where the belt is tensioned, it is called the driving strand, because the motor exerts the pull there. And up here, the belt on the top side, that is the slack strand, which represents the return path, so to speak. And if we look at this on a larger scale, I have brought a belt with me, as it is used, for example, in small industrial systems. Then it becomes clear. So I can pull on this, and since this is not rubber, it does not stretch excessively, but it does stretch by about 1 or 2%. And when I pull on the top side here, you can see that the belt hangs loosely underneath. This is exactly what we can observe, for instance, in this schematic representation visible on the monitor, where the belt sags on the bottom and is being pulled on the top in this specific instance. Let's stop the system. I want to show you something else. For this example, I am holding a V-belt in my hand, and I also have a V-belt pulley right here. Here we observe that there are no teeth this time, but instead, we have the corresponding shape for this wedge, because the V-belt runs in a wedge shape down here, and I am able to now place it onto this pulley. And now we can contemplate what truly occurs. If the tension is ideal, then we achieve an ideal transfer of power. But what happens, for example, if the tension is too low? Then, which is the case as I am demonstrating it here, it will simply slip over this surface. And the danger here is, for example, that it gets too hot and the heat destroys the belt. And furthermore, the power transmission is absolutely not ideal. The alternative scenario is if I apply too much tension here. So if the tension is excessive, then the motor requires a significant amount of force to pull this belt over here, to pull this belt across, and moreover, the entire system is subjected to heavy stress. The material fatigues very quickly, and so we have neither an efficient nor a long-lasting system. We must definitely avoid both conditions, insufficient tension as well as excessive tension. But how can we prevent this? For this, there are measuring devices, nowadays also very handy measuring devices, that do this either optically or acoustically. Because we can visualize this, if we look back at our system here, I could now go here with my finger and say, roughly speaking, the tension of this system is correct. But today we possess far superior methods to ascertain this, whether through sound or sight. Why acoustically? Well, the whole thing works according to the same principle as, for example, a string on a musical instrument. On a guitar, for example, we can tune the string, and the string vibrates at its inherent frequency. We are able to measure this natural frequency. And this natural frequency also correlates with the length of the belt and its mass per unit of length, per kilogram. If we know the units, we can determine the belt's tensile force via the frequency, and thereby have the opportunity to verify if we are within an acceptable tolerance range or if adjustments are necessary. We always need a measuring device and must perform a measurement. When we set up a system, it is briefly commissioned, then it runs in for a period, and after a short runtime, we must use a measuring device again. We must check if anything has changed, or if the system works. If something has changed, perhaps we need to adjust the tension, or can everything remain as it is? And it is important that such a system is checked repeatedly at maintenance intervals. We are checking to see if there have been any changes, if material fatigue is apparent, and if replacement is necessary. These measuring instruments are also required for that purpose. And I want to show you in this video what these measuring devices look like, what they can do, and how they function. Modern belt tension measuring devices are naturally capable of measuring not only small demonstration models like these here, but also belts as they are normally used in industry. And we can look at such belts here. So we have very clearly pronounced teeth here. And I can place a second belt over this one. We observe that it has a different length. However, the teeth themselves are identical in size, whereas another model possesses the length corresponding to the previously mentioned model. I set this down. However, here we observe that the teeth are larger. We have various selection possibilities here, depending on the required force and the necessary length. Other variations also exist, which we can observe right here. Here we have 5 V-belts arranged adjacently, meaning 5 belts running in parallel next to one another. All of these options are available, and we can measure all of these possibilities using a modern belt tension meter. I have brought an example of such a device with me. This is the PCE-BTM 2000A. It's especially interesting when I go to the top. To the end of this gooseneck, we see 2 openings here. On the one hand, an LED, and on the other side, a receiver. This indicates that we have an optical measuring instrument here, which sends out and receives light, subsequently processing the data accordingly. When I look at this device's display, a prompt instructs me to press the key to initiate the measurement process. I will proceed to do that now. I am beginning, and we can clearly read the natural frequency of the belt at the top and below that the belt tension in newtons. The device can evaluate the belt tension because we have specified the length of the belt. We see that displayed at the bottom, along with the kilograms per meter of the belt. And through physical formulas above that, it is possible to then calculate the belt tension. The handling proceeds as follows. I take the measuring head onto the belt, ideally positioned in the center where the deflection is greatest. And then I set the belt into vibration. We can read the measured values here clearly and easily. We also have the option to save up to 750 measured values in 15 groups, so that afterwards we can calmly evaluate which belts need to be retentioned or require maintenance. If we look at the device a little more closely, we have a menu function here, which I will now call up. And there we see at the top the most important point that we, as I explained, can define the mass and length here, thereby allowing the device to calculate the tension for us. And besides settings for memory and calibration, we then have various settings like date and time, which is important when taking measurements, so we can trace back when and where we were with which device. The device is capable of measuring belt lengths shorter than 10 meters, as well as frequencies ranging from 10 to 900 Hertz, the PCE-BTM 2000A model. I have brought the PCE-BTM 2000L here for you. A belt tension measuring device with the special feature that I have a very flexible measuring head. You can see, firstly, that the measuring head is connected up here to a socket, initially via a coiled cable, and then a gooseneck that offers flexible use, which I can bend here exactly as required. In order to reach under covers, for instance, or here in my demonstration setup, so that I can quickly reach underneath something here and still take measurements in areas that are normally inaccessible to me. The gooseneck is 25 centimeters long. And the measuring device basically works by me being able to start the measuring process down here. I can then place my measuring head onto the system and subsequently receive a measurement value which I can then evaluate and save into various categories. The device has the capability to store 750 measured values, and if we look here, we have the option in the menu to recall the memory again, organized in folders, allowing us to categorize the data and thus enable comparisons. When we regularly maintain and check systems, which we must do, so we can see the last value of this system. Are there big differences? Did it leave the tolerance range? And that is very important because preventative action through measurement is significantly less expensive than waiting until a belt drive has actually failed and requires replacement, leading to downtime. And these are all issues we can prevent if we possess such a measuring instrument, which can optically inspect the belt, such as the PCE-BTM 2000L. Let's review both devices together in an overview. First, the PCE-BTM 2000A. A belt tension meter designed for compact deployment scenarios featuring a tensioning neck, which can be mounted directly onto the unit and possesses a length of 16 centimeters. Then, the PCE-BTM 2000L, a belt tension measuring device with a coiled cable, which we can connect up here, and attached to the coiled cable is a 25 centimeter long gooseneck, allowing us even in challenging situations. In systems where we must reach underneath covers, we can still easily access the area to measure the belt tension. Both devices come with software, are delivered with software, and are operated with 3 AA batteries, which we insert in the back, guaranteeing long runtime. Wishing you well-running systems and a nice day.
Discover and order the latest measuring and test equipment now on www.pce-instruments.com.